Hello everyone and welcome back to episode 3 of Pytorch full course, where we are doing now training on the MNIST dataset. So we're going to make a whole neural network on the MNIST dataset, but we're not going to use any fancy layers or all. This will be for the next video. So this video is just making a simple neural network with linear layers, rel activation functions, and just showing you how you can use it on the GPU, how you can use a data loader object, and how you can do anything like that. Okay, so let's get started coding our neural network for the MNIST dataset. The first thing we need to do is to download the MNIST dataset, and they make it pretty easy for you to do it. So first, you have to import Torchvision. So if you look at what Torchvision is, you'll see that it's basically Pytorch but for vision. But enough on that. I'm assuming you have Torchvision installed. You can just do import Torchvision, import Torch, and I can just do Torch. Here I can just import them, and as you can see it works. I can just do Torchvision dot underscore version, and then also I can also do Torch dot underscore version underscore. So like this, I got my two versions, and now I can continue. So I have to use the dataset from MNIST, and I'm going to do from Torchvision dot datasets import MNIST. And now what I can do is I can say data train is equal to MNIST, and data test is equal to MNIST as well. And here I'm saying root is equal to dot slash, root is equal to dot slash, and over here I have this, so this is working. And finally, what I need to do is I have to say download is equal to true, train is equal to true. And here I say download is equal to true, train equal to false. So this is going to select the testing set. So this is training, this is testing, so this works. And finally, what I can do now is more stuff. So I can do transform is equal to the, and then I can pass in some transforms. So first, I'm just going to pass in no transform, and you'll see why I'll want to pass some transforms. So I'm just going to run it, and now you're going to see that if I do data train 0, I get this. So I get a pill image along with the number 5. So what I can do is I can just do data train 0, 0. So this is the first, and you know the second element in the tuple is just, well, the label itself. So this is a 28 by 28 image that is in the format of a pill object. So first, to convert that, I can use the toTensor method. So it's going to convert a pill image to a tensor, and finally from that tensor I need to do certain things with it, which is that first I'm going to make it so that it's flattened, because we're not going to use convolutional layers today. We're going to do that in the next video, or maybe further down this video. So once this is done, what I can do is that I'm going to say transforms is equal to something. So I'm going to say from Torchvision dot transforms import compose and toTensor. So these are the two transforms I'll use along with lambda. So I'm going to use compose, toTensor, and lambda, and you're going to see it's going to be pretty useful. So first I just do compose, and now I can put multiple transforms together. And now what I'll do is I'll say first convert to a tensor. So these transforms are only going to be applied to the first element of the tuple, that is the input. The output you cannot modify it for now. So you can only modify the input, which is the image. So the image has been converted to a tensor, which is just like a NumPy array but for Pytorch. And then I have to do a lambda. And this is just going to pass in a custom function of whatever I want. So here I can say whatever function I want. So I can say lambda image, and I can just do image over 255. And here I can add in one more lambda, lambda image, and I can say image.view 784. So this is just going to convert the image, instead of being 1 by 28 by 28 to a 784. And you're going to see what I mean. So first I'll comment that out, and we'll run it again. And now if you look at data train 0, 0, it still didn't apply, so I have to pass in over here, transform, and now you see it looks like a transform like this, right? So you know, they're not all zeros. For example, you can see some values over here, and they've all been divided by 255. So if I don't divide by 255, you'll see that what I get is this. So I get zeros, and then I get 0.1, 0.68, 0.99, and I'm just going to do a simple test, which is just look at the maximum. So dot max, and I get that the maximum is 1. So I already don't need to divide by 255. That was a mistake from my part, and all we need to do is just convert it to a tensor, and that's it. And now if you look at the shape, you'll see that the shape looks like this. So it's 1 by 28 by 28. I want to flatten that to become just 784, and to do that I just uncomment this line here, and it's just going to, you see, bam, transform it to a 784 line. So this is done, and I'm just going to show the code over here. So this is what the code looks like. So I got this and this and this, and now if I look at the label, it still works. So everything works, everything's good, and that's it. Now it's time for the next part. We have those digits and we want to classify them, so what we need now is to create our model. So I'm going to do as always from torch import nn, and now I can create my model. So class MNIST model inherits from nn.module, define init, self, super._init. Can't forget this. And now I have to do even more stuff. Just boilerplate code. Self.layer is equal to nn.sequential. So what's the first input? It has a shape of 784. So nn.linear 784. I'm going to say that that's going to map it to 512. So 512 and then nn.linear 512 to 512. And then what I'm going to do next is I'm going to say nn.linear 512 to 10. I'm going to say self.loss is equal to n.cross entropy loss, and add in some ReLU activations over here. n.ReLU and n.ReLU, and this is it. And now I have the loss, and I'm going to say self.optimizer is equal to optim.atom. I'm going to say self.parameters, and as always I can get it back up over here. So from torch import optim, I can just put it here, optim. And now over here I got the optimizer, I got the loss, I got everything, and I'm going to do the conversion to the GPU a bit later. So now I'm going to do define forward self x return self.layers x. That's it. And finally over here I have to do define fit self x y, and what I'm going to do is I'm going to say ypred is equal to self.forward x. Now I have to calculate the loss. I'm going to say self.loss between ypred and y, and this is a special kind of loss. This is the cross entropy loss, and it's special because if you look at it, you'll see that it only accepts the input first and then the target, and there's a reason why. So the input here has to be raw unnormalized scores for each class. So the reason why I was not activating the output layer is because the loss itself does not want you to activate it. So I'm just going to leave it be. So this is how it looks like. This is the loss, and I can continue. So loss is equal to this, loss.backward, and I'm going to say return loss.item. Now it's time for the optimizer. So every fitting step I zero the gradient, so I just empty it. So I'm just going to say reset everything to 0, the gradients, and then we can continue. So once these gradients are 0, I can start populating them by just doing loss.backward, and once I populated them, I can step. So self.optimizer.step, and that's it. So I got everything fit forward in it, and once I run this should work. And you see if I do MNIST model is equal to MNIST model, it works without a hitch. Alright, so now I'm going to show the next step, which is using the data loader. And to do that, you have to import it and use it. So that's literally it. So first you do from torch.utils.data import data loader. You take it, and you have to specify a batch size. So I can say the batch size is going to be equal to batch size and data loader. This is train and this is test. And if I just continue, data test batch size is equal to batch size, I can choose to shuffle or not. I can say sure, shuffle, sure. And here there are some options. I can choose to pin the memory, and I can also choose the number of workers and the collate thingy. So if you look at how it looks like, there's a lot of configuration you can do with the data loaders, and it looks like this. So I'll just go on the official documentation, and it looks like this. So you can pass in the dataset, that's what we passed. Then you pass in the batch size. So how many samples at a time will you take? Then whether you shuffle or not, the number of workers, whether you pin memory, and all that. So by default, I'm just going to let it be like this because we're still going to train on the CPU. I'm going to show how to train on GPU just a bit later. And this is it. So we have this. This looks perfect. This looks amazing. And I can run this. And you see I get an error. So I just have to define batch size. Batch size is equal to 32. So here's the code. Yep. So batch size was 16. We change it to 16 because it's a beautiful number. We usually take between 16, 32, 64, and 128, 256. So it's usually just multiples of 2 from 8 to like 256 is like the max I've seen. But sometimes people do like 1 million or whatever. I'm like, oh wow, this is a lot of batches. This is a huge batch. So we have this, and now we can iterate over it. So I can say for sample x, for x's in what? For x's, y's in data loader train. What I can do is that I can just say, well, MNIST model dot fit x's, y's. And here I can say loss is equal to this, and I can return it. So I can say print loss for now. So let's just do one pass and see how it works. Afterwards, I will do for I in range epochs, run this. So let me just tab it. I tabbed it, and now what I can do is I can say the epochs is, let's run it for 5 epochs. Let's have this loss. I'm going to have total loss is equal to 0. And then what I'll do is I'll just do total loss plus equal this, the loss that I got from here. And now I just need to do total loss divided by the number of batches. So divided by length of data loader train. And I can print it. So print epoch I, and then I put in the loss with 4 decimal places. So it looks like this. And I'm not even sure if it'll work in the first try. I'm pretty sure it will not work, but let's see if it works or not. So once I do this, it appears to be running. So we can wait a bit and see how it goes. Alright, so now it's finished running, and what I can do is I can evaluate it. So I can say for x's, y's in data loader test, what I'm going to say is that I'm going to predict MNIST model dot, I'm going to predict it. So MNIST model x's, and what I can do now is I can say without gradients, do something with it. But I'm going to be a bit, that was an oversight from my part. I'm going to create a new function here, which is going to be predict. So define predict self x, and it's going to predict it. So what I can do is I can do with torch.nograd. I have to import torch. So what this will do is that whatever inside torch.nograd will not have the gradient stored. So it's going to be more efficient, and it's going to use when you're not going to use it to fit the model. So when you're not fitting the model, put nograd on. So with torch.nograd, now I can predict this. I can say return self.forward x. But what I'm going to do is I'm going to add in one more step, which is just going to be taking the argmax out of it. So I'm going to say torch.argmax self.forward x, and I'm going to say axis equal to -1, and this will just make sure that it's going to be the last axis. And with this, it means that instead of having a list of scores for each digits across a batch size, I'll have across the batch size just a list of digits. So this is a 5, this is a 1, this is a 0, this is a 2, and so on and so forth. So this is done, and with this over here, I can put this, leave it. I'm creating a model again from scratch, and what I can do over here is do from tqdm import tqdm, and over here I'll just put in tqdm like this, and I'll say description is equal to fitting epoch I. And then you'll see that you get this fancy loading bar, which is very nice to have. I quite like having it. It makes you sound very cool. And as you can see, I forgot to put in the F over here, and that makes me look very silly. So if I rerun it again, bam. So this is good, I like it. And now we wait. Alright, it has finished running. So as you can see at the last line, I have a loss, cross entropy loss of 0.04, which is pretty good, pretty low, I like it. Now it's time to predict. So here, for x's, y's, and dataloader test, blah blah, I'm going to say MNIST x's, and I'm going to get a list of labels. If I just print this, I want to see how it looks like first. So if I print this, I get a tensor with 80015. Okay, so this looks good. And now, if I print y's, what I get is this. So I can see it shuffles it every time. So hey, our model's pretty good. Looks like it matches everything here on the testing set. So this is only a small sample of the test set. Now what we have to do is make our own accuracy score. So I'm going to say correct is equal to 0. And here I can say y's is equal to ypred. And then if I just do ypred is equal to MNIST model.predict x's, what I get is this, true, and I have one false. If I rerun again, you see I have one false again. Here I have all true, so it's mostly true. And if I just do a sum now, you see that now I get 16. So this is just going to be the number of times it was correct. So now I'm just going to say correct plus equal this thing here. And finally, at the end, I can just say print accuracy is equal to, well, accuracy. And I didn't calculate it yet. So I can just do accuracy is equal to the number correct over the total number of samples. So how many samples do I have in total? I believe that I have len data loader test times batch size. So once I run this, you see that I get a testing accuracy of 97%, which is super good, super cool. I like it very much. So if I just look at the length itself, it should be, you see, 625, and remember, before it showed that it was 10,000. So 625 batches of 16 gives 10,000. Do it? Does it? Let me just verify. Yeah, so you see 725 times 16 gives 10,000. And here we successfully built our MNIST model to have an accuracy of 97% on a testing set, which is super awesome. Now I'm going to show how you can port this to GPU. It's very simple. All you need to do here is first I'm going to define a little utility that will be called 2t. And I can just do define 2t like this. It's going to accept a tensor, and what it's going to do is that it's going to say device is equal to get default device, and I'm going to make the function itself. So define get default device. It's going to be return torch.device.cuda if torch.cuda.is available. I'm not sure if this works, so I'm just going to state what I know. So like this, cuda, else torch.device CPU. And over here I can just say return tensor.to the device it is, so .to device. And that's it. So with this here, I also need to put it over here to port the whole MNIST model to GPU by just doing self.to, and then here I say get default device. And over here, forwarding, predicting, I also have to make sure that they're correct. So I'm not going to do that over here. I'm going to do that in the training loop and in the evaluation loop. So this is done. I can run this. I can run this once more. I'll run this once again. And over here, for each time I get the x's and the y's, I'll just say this will be our x's and our y's for raw x's and raw y's. And what I'll do now is just do x's, y's is equal to 2t r x's, 2t r y's. So now everything is ported to GPU, and here for my evaluation loop I have to do the exact same thing. So I have to say, I'll do that this is the raw x's and this is the raw y's. Now here I can say x's is equal to 2t r x's, and I'll say x's y's is equal to 2t r y's, like this and like that. So I run this again, and now you see this is clearly much faster than my CPU. And we'll just wait a bit. We still have to wait even though if I'm using my GPU. Alright, it's done running, and now I can run it again over here. And what I get right now is accuracy of 97.66. So same thing. I'm pretty sure the last training digits are a bit different, whatever. But just trust me, we've used it on the GPU. It was much faster than before. And that's it. That's essentially how you can run Pytorch, create a model on it, put it to GPU, and do everything. So see you in another video, and I hope you enjoyed this video. The sun is setting down because of how much time I was filming. So goodbye, thank you for watching, and see you in the other Pytorch video.